Now I'm going to show you the textbook's way of doing integration by substitution. So let's say you've got y equals 3x. So this is a straight line of gradient 3. And let's say you've got y equals x squared, which looks like this. When you differentiate this, it will give dy by dx equals 3. So I do have the right to times both sides by dx. So what that means is, you know the gradient is 3. You know the gradient is 3. So if you get this length here, let's just imagine it to be 1. Then when you get, so dx, let's just imagine dx is 1, the width is 1, and then you times it by this magical gradient, then it will give you the change in the y. It will give you the height. So when you have a gradient of 3, if you times it's both sides by dx, it will then give you this, and then when you get the change in the x direction, and then you multiply it by this magical number, it will give you the dy. It will give you the dy. My point is that when you start with this, you can just jump. You can just take the differential of both sides. So you can just jump to dy equals, differentiate this, which would be 3, and then dx. So you can just jump to here straight away. And if you feel uncomfortable with this, you can differentiate it and then times both sides by dx. So what that means is a small change in x. If you times it by the gradient, then it will give you the change in the y. So now let's migrate to over here. When you differentiate this, it will give you 2x. You do have every right to times both sides by dx. So it will then give you this thing here. So what that means is, depending on where you are, let's say x is here. If you get this delta x, this dx, and then you multiply it by this magical gradient, it will then give you the change in the y direction. Let's say x is over here. So let's say x is over here. If you get this delta x, and then you multiply it by this magical gradient, it will then give you the change in the height. So when you're here, you can actually imagine this as being delta y. Imagine this as being delta x. So delta y is the same as, depending on where you are, 2x, and then you times it by delta x. If you get delta x, multiply it by this magical gradient, it will give you roughly, sorry, this should be approximately, it would be approximately the change in the y. When you're here, you've got to imagine delta y as being like, in your mind, picture delta y as being a really small number, let's say 7. And then when you're here, imagine delta x as being a really small number. Let's just imagine 0.00, I don't know, let's say 3, say. When you see at the moment, this thing here is approximately equals to dy, the change in the height. But when you take the limit as the delta tends to 0, then this delta y becomes dy, and this delta x here becomes dx. So dy, imagine it as being a small number, and then dx, imagine dx as being like another small number. But when you take the limit as the delta tends to 0, as it gets really small, so you're zooming into this, you're zooming into this, you're zooming into this, delta y becomes dy, delta x becomes dx. So when you get to this stage here, when you take the limit as delta tends to 0, you've got to imagine dy as being, well, up here you've imagined dy as being 0.007, say. When you get to this stage here, when the limit tends to 0, you've got to imagine dy as being a really small number, because here you're actually migrating from an already small number to an even smaller number. So imagine this as being, I don't know, let's say 7.3 here, and then here delta x is already small. When you take the limits as delta tends to 0, this thing here, you got to in your mind, you got to picture this as being a really small number. So this delta x, you got in your mind, you got to picture it as being 0.000000000, I don't know, let's say 1/8, say. So the point here is that here is already a small number, which is approximately this. So when delta x and delta y are small numbers, you can say, oh yes, it's approximately this. But when you start to take the limits as delta, as the two deltas tend to 0, you can actually say it equals precisely this thing here times the magical gradient. It will give you the change in the height. So my point here, the whole point of this thing here is that when you're here, you do have every right to jump to dy equals 2x dx. You do have the right to jump to this straight away. Okay, so in the next video, or well, I'm going to do it now. So integration by substitution, you notice that this thing here is a derivative of this thing here, because when you differentiate to the power of 3, it will give you 3x squared. So notice this x squared is pretty much the same as this. We can negate this 3 later on. So hang on. So to integrate this, let u be this thing here. So let u be this thing here. So now du equals, well, I'm going to differentiate this. This will be 3x squared dx. So I do have every right to jump from here to here. So du equals this thing here. But see this dx here, I want to get dx on its own. I'm going to divide both sides by 3x squared. So so that will then take me to here, and then by doing u substitution, integration by substitution, I can put this into the dx, which is this thing here, and see this bubble here, I can put u into there, so that would be u to the power of 5. This x here, I'm just going to leave it for the time being, and then notice that this will get cancelled out with this, and then you still got your third here, and then you've got your u to the power of 5 du. So now you can integrate everything with respect to u. That's the whole idea behind u substitution. So now this is just a constant. It has nothing to do with u. So you can take it out. So that will then give you this. So now just concentrate on the integral part. So now integrate this. It will give you this, and then tidy this up. It will then give you this thing here. Well, don't forget u here is really this thing here. That's u. So you can put this into the u, into the u, giving you this thing here. So your final answer is this. Okay.